Welcome to The Explainer. Today, we are going to pull back the curtain on a hidden mathematical code. I'm serious. It's everywhere in your daily life, from your savings account all the way to the seats in a stadium. Ready to crack the code? Let's dive in. So take a look at these. At first glance, right, they seem totally unrelated. But believe it or not, they all share this secret mathematical structure. Okay, let's start with something you probably know well: planning your savings. Think about it. You deposit, say, $100 into your bank account every single month. That balance, it grows in this super predictable way, doesn't it? Or what about this? You're stacking chairs for an event. The height of that stack grows with each chair you add, right? And that little bit of extra height you get with each chair. It's the exact same, every single time. And you've definitely seen this one, the way seats are set up in most theaters. Each row has a few more seats than the one in front of it. There's a really clear, really consistent pattern going on there. So what's the big secret here? What connects all of these things? It's just a simple, predictable pattern of constant change. And trust me, once you see it, you're going to start noticing it everywhere. All right, so this pattern actually has a formal name. It's called an arithmetic sequence. All that means is it's a list of numbers where the value changes by the exact same amount with each step. No tricks, no funny business, just steady, constant progress. And that constant amount, that's the key to the whole code. It's called the common difference, and we usually just use the letter D to represent it. Finding this D value, well, that's everything. It's really the engine that drives the entire sequence forward. Now, what's really cool about this common difference D is just how flexible it is. It can be a positive number, right? Making the sequence grow, just like your savings account. Or it could be negative, making things decrease, kind of like when you're gradually reducing a medication dose. It can even be a fraction or a decimal. The only rule is that it has to stay the same. Okay, so once you've found that common difference, you basically unlock a superpower. You get this powerful tool that lets you predict any term in the sequence without having to write out the whole boring list. This is where the math gets really cool. And here it is. This is the prediction formula. Now, I know, it might look a little technical, but it's actually just telling our story in math language. To find any term, we'll call it AN, you just start with the very first term, A1, and then you add that common difference, D, a whole bunch of times. How many times? Well, it's just one less than the position of the term you're looking for, or n minus 1. Let's put this thing to work with our auditorium example, okay? So the first row has 35 seats. That's our A1. And we know we add 4 seats per row, so that's our D. Now, let's say we want to find out how many seats are in the 10th row, so n is 10. We just plug those numbers into our formula. A little bit of quick math shows, yep, the 10th row has exactly 71 seats. See? No guesswork needed. That is the power of this formula. All right, so finding any single term is pretty awesome. But what if we want to, add them all up? Like, what's the total number of seats in the first 10 rows? Well, there's a really elegant trick for this, and it was famously discovered by a young student who would go on to become one of the greatest mathematicians in history. Yeah, the story goes that his teacher gave the whole class this pretty tedious, busy work, probably thinking it would take them ages. But this kid, a young Carl Friedrich Gauss, he saw a shortcut, a pattern, and he solved it almost instantly, totally blowing his teacher's mind. So, how on earth did he do it? It's actually a beautifully simple idea. First, he just wrote down the list of numbers, 1 all the way to 100. Then, right underneath it, he wrote the exact same list, but backwards. And here's the brilliant part. He started adding the numbers in each column vertically. So, 1 plus 100, that's 101. Then 2 plus 99, also 101. 3 plus 98, you guessed it, 101. Every single pair added up to the exact same number, 101. Since there were 100 pairs, the total sum of all those pairs was just 100 times 101. But hang on, he used 2 lists, so that answer is double what he actually needs. So the final genius step, he just divided the whole thing by 2. And that clever little trick gives us this universal formula for the sum of any arithmetic sequence. You just take the number of terms, n, and you multiply it by the sum of the very first term and the very last term. Then, just like Gauss did, you chop the result in half. Okay, but here's something really important to keep in mind. Not every sequence that looks like a pattern is an arithmetic one. There's another really common type out there, and you gotta know the difference because it's key. The distinction is actually super simple. Arithmetic sequences, the ones we've been talking about, they're built on addition. This gives you that steady, linear growth. If you were to graph it, it would just be a straight line. But geometric sequences, they're built on multiplication. And that creates this rapid, exponential growth that curves up like a rocket. So think of it this way. It's the difference between taking steady steps versus making explosive leaps. So what's the big takeaway here? Well, it's that these simple additive patterns are literally all around us, shaping our finances, our buildings, you name it. And now, with just 2 simple formulas, you can understand and predict them. Now that you know how to spot this hidden code, the real question is, what other codes are out there, hiding in plain sight, just waiting for you to find them?